So today we are going to discuss another problem on root locus. Here the question is, draw the root locus of a unity feedback system having open loop transfer function g of s into h of s is equal to k divided by s plus 2 divided by s k into s plus 2 divided by s square plus 2s plus 3. So we have to plot the root locus. Here they have given us it's an unity feedback system and open loop transfer function g of s h of s is also given. So we know that for a unity feedback system h of s is equal to 1. So open loop transfer function g of s h of s is actually equal to g of s only. Now we have to find out the first step is to find out the number of poles. Okay, so here we can see that the number of open loop poles n is equal to 2, since in the denominator there are the highest power of s is only 2 and number of open loop zeros is m is equal to 1 because there is a term s plus 2 that is present in the numerator. So we have number of open loop poles is equal to 2, number of open loop zeros is equal to 1. So how many root locus branches will be there? The root locus branches, the number of root locus branches will be equal to 2, that is equal to the number of open loop poles, in which one branch will end at the two root locus branches should end at should terminate at 0. So here, since we have a finite 0, one root locus branch should end at the finite 0 and the other root locus branch should end at a 0 that is at infinity. Okay, so there are two root locus branches. From the two poles there will be two root locus branches that is starting, and one will end at the 0 that is a finite 0, and other will end at a 0 that is at infinity. Now we can write the location of poles and zeros. So on solving the equation s square plus 2s plus 3, we will get the location of poles, open loop poles. The location of open loop poles are at s is equal to minus 1 plus or minus j root 2. Okay, or that is minus 1 plus or minus j 1.4. that is the location of open loop poles, and the location of open loop 0 that we have s plus 2 is equal to 0, that means s is equal to minus 2. So the next step is we can plot the location of poles and zeros in the graph sheet. So I have plotted two poles, that is at minus 1 plus j 1.4 and minus 1 minus j 1.4 in the graph sheet that you can see here as cross signs, and also I have plotted the 0 that is at minus 2. Okay, that is indicates with a circle. Now the next step is, what is the next step? The next step is we have to determine whether there is any part of real axis that is included in the root locus, that we have to determine. So for that, what we have to do is we can check, we can take any arbitrary points and we can check whether there is any we can check the total number of poles and zeros to the right part of that arbitrary point. So first test point is minus 1. So from minus 1, check to the right hand side of minus 1. So if we check the right hand side of minus 1, you can see that there are no real poles and zeros to the right hand side of minus 1, to the point minus 1. That means this minus 1 point, that is not included in the root locus. Now we can check another point, that is at minus 3. Okay, we can check at minus 3. So check to the right side of this point minus 3. So we can see that to the right side of minus 3 there is one real zero. The total number of real poles and zeros to the right hand side of minus 3 is 1. That is an odd number. That means this minus 3 point is included in the root locus. Again we can check another point minus 4 and check to the right hand side of minus 4 what is the total number of real poles and zeros. So then it will be also 1, that is again an odd number. So if you check any point from this minus 2, if you take any point like minus 3, minus 4, minus 5, etc., to the right hand side of that, the only real poles and zeros, the total number of real poles and zeros are equal to only 1, that is the real zero at minus 2. That means from this minus 2 to infinity, this segment, that is the line segment in the real axis, that is starting from minus 2 to infinity, that is included in the root locus. So we can first plot the real axis part. So we can see that from minus 2 to infinity, this line segment is included in the root locus. So we know that we will draw the root locus. So from minus 2 to infinity, this segment is included in the root locus. Okay. So does that means the root locus branch starting from the 0 minus 2? No, the root locus will not start from a 0. It will only terminates to the 0. So it only indicates that from minus 2 to negative infinity, the real axis line segment is included in the root locus. That doesn't mean that the root locus branch starts from the 0. Doesn't mean that the root locus branch starts from 0. It only indicates that that part, that is starting from minus 2 to negative infinity, is included in the root locus, and we know that the root locuses will starts from only poles. So we already have two poles, that are two complex conjugate pair of poles are there. So the next step is we have to find out the angle of asymptotes corresponding to. So we know that since there are two root locus branches and there is only one zero, one root locus branch that will end at the 0 at minus 2, and other root locus branch will go to 0, that is at infinity, that go asymptotically. So we have to find the angle of asymptotes. So in order to find the angle of asymptotes, we can write the equation plus or minus 180 into 2q plus 1 divided by n minus m. Here n is equal to 2 and m is equal to 1. Q is equal to 0, 1, 2, etc. up to n minus m minus 1. So what is n minus m minus 1? That is 0. So you need to check only q is equal to 0. So at q is equal to 0, the asymptotes, angle of asymptote is plus or minus 180 degree. So what is plus or minus 180 degree? That is, we already got that the root locus branch that starts from the root locus part, that is from minus 2 to infinity, is included in the root locus. Hence the angle of asymptotes plus or minus 180 indicates that this part, okay, the angle of asymptotes that indicated by plus or minus 180 degree is actually this part. That means one root locus branch that will end at that will start from any of the poles will end at infinity through the negative real axis, and the angle of asymptotes are plus or minus 180 degree. Now centroid, we can find the equation of centroid because each asymptotes will meet the real axis. So in order to find the equation of centroid, that is sum of poles minus sum of zeros divided by n minus m. So what is sum of pole? Sum of poles are minus 1 plus j root 2 and minus 1 minus j root 2. So sum of pole is at minus 2, and sum of zeros, that is again at minus 2. There is a 0 at minus 2 divided by n minus m, that is 1. So the centroid is 0. That means we can just draw the asymptotes plus or minus 180 degree starting from this point 0. S is equal to 0. Starting from the point S is equal to 0. So here no need to draw the asymptotes because the asymptotes are at in the negative real axis, that is at plus or minus 180 degree. So no need to draw the asymptotes here because it is actually at the asymptotes are at the negative real axis. Now we have to find the breakaway points. So we know that there will be two root locus branches that starting from these two poles, and that should meet at some point here, okay, because one root locus branch should end at a 0, that is at minus 2, and other root locus branch should end at a 0, that is at infinity in the negative real axis. So we have to find whether there is any breakaway point or breaking point. For that we have to find the characteristic equation of the system. So use the equation g of s divided by 1 plus g of s h of s, and by that we can find the characteristic equation of the system is s square plus 2s plus 3 plus k into s plus 2 equal to 0. From that the value of k is equal to s square plus 2s plus 3 by s plus 2. Now in order to check that whether there is any actual breakaway point or break-in point, we have to find the equation dk by ds equal to 0. So find the first derivative of k with respect to s. So that will be k is equal to minus of s square plus 2s plus 3 by s plus 2. Now dk by ds, for that minus of s plus 2 into 2s plus 2 minus s square plus 2s plus 3 divided by s plus 2 whole square, which is equal to 0. Now on solving the equation we will get on solving the equation we will get 2s square plus 6s plus 4 equal to s square plus 2s plus 3. That means s square plus 4s plus 1 equal to 0, where s is equal to minus 3.73 and minus 0.26. So these are two values of s. So we know that if there is a breakaway point, that breakaway point should come, that breakaway point should be on the root locus. That is, the we already have the line segment that is starting from -2 to infinity is a part of root locus. That means the probable breakaway point here is only -3.73, because the point -0.26 is not included in the root locus. We know that from 0 to -2, this line segment is not included in the root locus. So this -0.26, that is actually lying on the line segment 0 to -2, which is not included in the root locus. So the probable breakaway point is -3.73, but we need to check whether it is an actual breakaway point by substituting in the equation of k. So substitute in the equation of k, s is equal to -3.73, which you substitute in the equation of k, that is minus of s square plus 2s plus 3 by s plus 2, then you will get plus 5.4. Since when you substitute the value of s -3.73 in the equation of k, you get a positive real number. That means that s is equal to -3.73 is a breakaway point. Okay, breakaway point. Now s is equal to -3.73 is a breakaway point. Now if you substitute the value of s, that is -0.26 in the equation of k, you will not get k as a positive real number. So the actual breakaway point is at -3.73. So you can mark that -3.73. So this is our breakaway point. Now what is the next step? The next step is we have to find the angle of departure and angle of arrival. Since we have a complex pole, we have a pair of complex poles. Since we have a pair of complex poles, there will be only angle of departure. Angle of arrival is associated with pair of complex zeros. So here there are only complex poles, that means there will be only angle of departure. So what we have to do in order to find the angle of departure, you can plot straight lines. So consider a complex pole A. Okay, consider a complex pole A. I am considering this as my complex pole A. So to this complex pole A, mark straight lines. So we can draw straight lines from all poles and zeros to the complex pole A. So we only have 2 poles and 1 zero. So one is this complex pole A. So from the complex conjugate pair, that is a complement, from the complex conjugate pair of other pole, that is a complement, we can mark a straight line. So that is this straight line, and from the -2 0, we can also mark another straight line to the complex pole A. Now we have to find out the angles corresponding to the horizontal axis. So here we know that the angle corresponding to this angle will be 90 degree, theta 1, that is equal to 90 degree, and this angle theta 2. Okay, in order to find out theta 2, you can measure using protractor. Okay, you can measure using protractor. In order to find out theta 2, you can measure the angle theta 2 using protractor. Now the angle of departure is I have already told you the equation for angle of departure. Please check that. 180 minus theta 1 plus theta 2. This is the angle of departure. So if you check the angle of departure, you will get theta 1 is 90, 180 minus 90 plus theta 2, you will get theta 2 as 35 degree. So the angle of departure is plus 125. The angle of departure is plus 125 corresponding to the complex pole A. Now if the angle of departure corresponding to the complex pole A is plus 125, angle of departure corresponding to the other complex pole, that is A complement, will be minus of plus 125, that will be minus 125 degree. So we got angle of departure, and now we can plot the angle of arrival and angle of departure here corresponding to the complex pole A. So plus 125 will be approximately here, plus 125 degree, and minus 125 degree will be approximately here, minus 125 degree. Now we know that there will be two root locus branches, starts from A, and the root locus branches starts from A and A complement, two poles at k is equal to 0, and one will go to s is equal to minus 2 0, and one will go to the 0, that is at infinity, when the range of k varies from k is equal to 0 to infinity. So we can draw the root locus branches. So the angle of departure from complex pole A is minus 125. So it will go to this point, and here it is minus 125, then it is go to this point, and after that it will come to the breakaway point at minus 3.73 from both sides. It will come to the breakaway point at minus 3.73. okay, and after this breakaway point, one root locus branch will go to 0, that is at infinity, and other root locus branch will go to 0, that is at s is equal to minus 2. So this is k is equal to 0. From k is equal to 0, the root locus branches starts from this point, that is A and A complement, at k is equal to 0. Then after that, when the value of k increases, one root locus branch will go to infinity at k is equal to infinity, 0 to infinity, and other will terminate at s is equal to minus 2, and the value of k is at infinity, 0 to infinity. So this will be the approximate shape of our root locus. Now since we don't have any root locus part, that is on the LHS, that is on the RHS, the all root locus branches are lying only in the LHS or left hand side, we can say that the system will be stable for all values of k, because when the value of k starts from 0 to infinity, the root locus is only lying on the LHS. We can say that the system is stable. The system is stable for all values of k starting from 0 to infinity. That is our inference, because the root locus not crosses the j omega axis, it is actually lying in the LHS only. Now we know that when k is equal to 0, our root locus branch starts from these two complex poles, and after that when k is equal to 1, there will be some value of pole will be there, and after that at some point it meets at the real axis. Okay, when s is equal to minus 3.73, that is at breakaway point, it meets at the real axis. So before that, at any value of k, before s is equal to minus 3.73, we already find out the value of k at s is equal to minus 3.73, that is the value of k is 5.4. So when the value of k less than 5.4, when the root locus meets the real axis, the value of k is the value of k is 5.4. That means that when the value of k, which is less than 5.4, when the value of k is less than 5.4, you can see that if you check your root locus, the system poles will be complex, because at k is equal to 1, some 2 poles will be there, and at k is equal to other 2 poles will be there, etc. And when the value of k is less than 5.4, the poles of system will be complex, because we are plotting the root locus, that is the locus of roots of the closed loop system. So when the value of k is less than 5.4, the roots may be at some point will be this and other point will be this, hence there will be complex conjugate poles. And when the poles are complex conjugate pair, the system will be under damped. Okay, that we have already studied in second module. That means when k is less than 5.4, the system will be under damped system. And when the value of k reaches 5.4, at this point, that s is equal to minus 3.74, when the value of k is at 5.4, it means the two root locus branches meets at this point, and the system is having repeated poles. At this point, the system is having repeated poles. Or when the value of k greater than or equal to 5.4, the system is having repeated poles. What do you mean by repeated poles? When the system is having repeated poles, since this is a second order system, we can easily say that when we have repeated poles, the system will be critically damped, or the value of zeta is unity. So the inference is that when the value of k is less than 5.4, the system will be under damped system. When the value of k greater than or equal to 5.4, the system will be critically damped system, or the zeta value is unity. And corresponding to some particular pole for a second order system, we have already studied for a second order system. Okay, so like this, if two complex conjugate poles like this are present for a second order system, draw straight lines from 0 to this second order to these complex conjugate poles. This we already studied in the second module. This part is omega d, j omega d, its value is omega d, and what will be this value? This value will be theta omega n. Okay, so this straight line, vertical line, the value will be omega d, and this will be theta omega n. And what is omega d? Omega d is equal to omega n into square root of 1 minus theta square. You can see that this is a right angle triangle, and this will be, you can solve this right angle triangle, and this part, that is hypotenuse, will be omega n, and this value, that is theta, we can see that cos theta is equal to theta omega n by omega n, that is equal to theta. So if you got a problem for second order system, if you want to find out the theta for some particular pair of complex poles, you can draw straight lines to that complex poles and measure this angle theta, and cos theta will give you the damping ratio theta, because cos theta is equal to theta. So if a second order system like this is given, you can easily find the damping ratio using this. So for this system there are 2 poles and 1 0. So there will be 2 root locus branches. One will end at the 0, that is at infinity, and one will end at the finite 0. Thank you.